Your air conditioner is lying to you, not about the temperature, not about the fan speed. It's lying about how much power it actually needs to do its job, and it has been doing it since the day it was installed. And here's the part that's going to stay with you long after this video ends. The fix costs less than $2. It fits in the palm of your hand. The electrical engineering behind it has been understood since the 1950s. And yet, almost no one outside of industrial electrical circles has ever been told about it. So why don't you know this? That is exactly the question this video is going to answer. Not in a vague, hand-wavy way. In a precise, logical, step-by-step way that will make everything about your power bill suddenly make sense. Stay with me through the first few minutes because the setup matters and the payoff is real. Let's start with something your power company knows about your home that you almost certainly don't. When electricity flows into a building, not all of it is doing useful work. This sounds like it shouldn't be possible. You're paying for electricity is flowing, things are running. What do you mean it's not doing useful work? This is exactly the misconception that costs residential customers money every single month. In a simple resistive circuit, a toaster, a space heater, an old-fashioned incandescent light bulb, the relationship between power consumed and power billed is basically 1-to-1. What flows through the meter gets used. Clean, simple, efficient. But your air conditioner is not a toaster. Your AC unit runs on an inductive motor. That's the compressor, the heavy mechanical heart of the system, the part that does the actual work of moving refrigerant and cooling your home. Inductive motors behave in a way that is fundamentally different from a resistive load. They don't just consume power, they borrow it. Every cycle of alternating current, the motor draws in a surge of electrical energy, uses part of it to build and collapse a magnetic field, and then sends the portion it didn't use bouncing back toward the grid in a kind of continuous, invisible, wasteful pulse. Electrical engineers call this reactive power. And reactive power is the quiet thief that has been running up your electricity bill for years without you ever knowing it had a name. Here's where the meter comes in. And this is the part most people have never thought about. Your electricity meter measures what's called apparent power, not just the useful working power your appliances actually consume, but the total flow of current through your system, including all of that reactive power your motor is borrowing and returning. Every ampere of reactive current that flows back and forth through your meter without doing any real work in your home is potentially appearing on your bill. This relationship between real power and apparent power has a number. Electrical engineers call it power factor. A perfect power factor is 1.0. Everything flowing through the meter is doing actual work. Nothing is wasted. A typical residential air conditioner compressor, its power factor often sits somewhere between 0.6 and 0.8, depending on age, motor design, and operating load. That gap, that 20 to 40% of current that's oscillating uselessly in your wiring, is the invisible overhead charge baked into your electricity bill every single summer. And here's the strange part. This is not new information. Power factor isn't some obscure theoretical concept buried in graduate-level physics. It's a standard foundational principle in electrical engineering. Large factories deal with it every day. Commercial office buildings, hospitals, also industrial plants. They all invest in power factor correction equipment because the savings are significant enough that in some countries, regulators require it. There are international standards for it. There are entire product categories built around it for industrial use. But in your home, almost nobody talks about it. So, what's the fix? The device at the center of this is called a capacitor. Before you skip past the technical term, here's all you actually need to understand. A capacitor does almost the exact opposite of what an inductive motor does. A motor pulls in reactive current, builds a magnetic field, and sends the unused current back. A capacitor stores electrical charge and releases it in a way that counters the returning pulse. It absorbs the reactive current before it bounces back through your meter. When you connect a properly rated capacitor in parallel with your AC compressor, meaning right alongside it in the circuit, something elegant happens. The reactive current that used to flow all the way back to the grid now gets absorbed and recirculated locally, right at the unit. The motor and the capacitor essentially feed each other. The motor pushes reactive current out. The capacitor catches it and feeds it back in. The wasteful oscillation is resolved before it ever reaches your electricity meter. What now flows through the meter is much closer to pure, real, working power. Your compressor draws fewer amps from the grid. It runs at a more efficient operating point. The heat generated in your wiring goes down, the motor runs cooler, and in some configurations, people report measurable reductions in their electricity consumption during peak cooling months. The component that makes this happen, a run capacitor, costs between $2 and $20, depending on the specification and where you buy it. The principle behind it has been documented since before most of the people watching this video were born. So why doesn't everyone know this? Here's where the story gets genuinely interesting and genuinely a little frustrating. The practical understanding of power factor correction using capacitors in residential settings was not suppressed in some dramatic way. There was no memo, no official policy. What happened is something more subtle and more common in the history of practical knowledge than most people realize. By the mid-20th century, electrical engineers working in industrial settings had thoroughly documented the benefits of capacitive power factor correction for motor-driven loads. The mathematics was settled. The hardware existed. And there were people in the 1950s and 1960s who explored whether this could be packaged economically enough for household use. What those efforts ran into was structural inertia. Residential electricity pricing in most markets had been built around billing for apparent power, the total metered current, reactive and real together. Utilities had constructed their entire revenue model around that billing structure. If millions of households suddenly corrected their power factor, the total metered consumption would drop, without any reduction in actual comfort, actual appliance function, or actual service provided by the utility. That's not a problem the power company was eager to publicize a solution for. Again, this is not a dramatic conspiracy. It is simple economics. Industries protect structures that benefit them. The technology was never hidden in any active sense. It just never received a consumer-facing marketing campaign. It never got packaged into something you could buy at a hardware store with instructions printed on the box. It stayed in industrial supply catalogs, in HVAC technician manuals, in the back of the napkin calculations of old-school electricians who learned it on the job. And those electricians? Some of them quietly passed it on to clients, to apprentices, to the people who knew enough to ask the right questions. Today, this knowledge still circulates in electrical forums, HVAC communities, and among the kind of people who actually read the motor nameplate before they call a repairman. But the average homeowner pays their monthly bill. They have no idea this conversation exists. Let's talk about what the real-world impact looks like, because this is where it gets concrete. The actual savings any individual household sees depend on several variables. How poor is your existing motor's power factor? How does your specific utility structure its residential billing? What is the capacity and condition of your current run capacitor? These factors vary. Anyone who gives you a universal percentage with total certainty isn't being fully honest. What we can say is this: for homeowners in regions where residential meters measure apparent power, which is more common than most people realize, particularly in certain utility districts, co-ops, and international markets, correcting the power factor on a major inductive load like an AC compressor can produce a meaningful, measurable reduction in metered consumption. Some homeowners who have installed correctly sized run capacitors on aging AC systems report AMP draw reductions of 15 to 30% under load. But here's something even more interesting than the energy savings, because it speaks to a benefit that never appears on a bill. A motor running with a poor power factor isn't just expensive, it's physically stressed. The reactive current flowing through the windings generates heat. The motor is working harder than the actual cooling load requires. Over months and years, that excess heat degrades the insulation on the motor windings, accelerates bearing wear, and increases the likelihood of startup failures, particularly on hot days when the motor is already working near its load limit. When you correct the power factor, you're not just reducing the number on your electricity bill. You're reducing the thermal stress on a major mechanical component. You're potentially extending the life of an appliance that costs thousands of dollars to replace. This is why HVAC technicians who understand this principle often recommend it not just as a cost-saving measure, but as a maintenance strategy for aging systems. So what does the actual application look like in practice? The key component is the run capacitor. This is a cylindrical metal can, usually found in the electrical compartment of your outdoor AC unit, the part that sits outside your home. Most central air systems use what's called a dual run capacitor, a single component that serves both the compressor motor and the fan motor. It will be labeled in microfarads, usually on the side of the can. The nameplate on your AC unit, typically attached to the side of the outdoor cabinet, lists the specifications for your system, including voltage ratings. The existing run capacitor will also have its rating printed on the body. These numbers are your starting point for matching a replacement or supplemental component. In many older systems, the original run capacitor has degraded over the years of heat cycling and electrical stress. A capacitor that has lost capacity no longer corrects reactive power effectively. The motor is effectively running without power factor correction at all, borrowing reactive current and sending it straight back to the grid. Simply replacing a degraded capacitor with a fresh one of the correct rating can restore the efficiency the system was designed to operate at. For a more active supplemental approach, some electrical professionals install a small additional capacitor in parallel with the existing system, a configuration that has been discussed in electrical engineering literature for decades and is still practiced in various forms in markets where residential power factor awareness is higher. One important note, and this matters, any work involving high voltage AC systems requires proper precautions. Capacitors store electrical charge even after the power is shut off, and they must be safely discharged before you handle them. This is a well-documented, straightforward process, but it is not optional. If you are comfortable with basic electrical work and safety procedures, this is an approachable project. If you're not confident, a qualified HVAC technician can evaluate your run capacitor and the overall efficiency of your system during a routine service call. The cost of doing this right is minimal. The cost of doing nothing is paid out in small increments every month on every summer bill for as long as the system runs. Here's the thought I want to leave you with, because this goes beyond air conditioners. There is a version of your home that is identical in every way to the one you're living in right now. Same rooms, same appliances, same temperature, same comfort, but it consumes less electricity meaningfully. Not because you renovated, not because you bought all new appliances, but because the invisible relationship between your motors and the power grid has been corrected by a small, inexpensive component that has existed in electrical supply shops for 7 decades. The knowledge exists, the hardware is cheap, the physics is settled. The only thing that has kept this from being common household knowledge is that the people who would benefit most from telling you, the people selling you electricity, have had no reason to bring it up. Every month without power factor correction on an inductive load is a month where the reactive current dance between your motor and the grid is playing out through your meter. And now, for the first time, you understand what that means. And what to do about it. That is the 2 trick. That is why it matters. And that is why old electricians still talk about it in hushed tones, while the rest of us pay full price. If this changed how you think about your home, hit like and subscribe. There are more of these hiding in plain sight, and we're just getting started.